Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Gauss Divergence Theorem, which comes under the topic Vector Integral Theorems. And today's overview of my presentation, first I'll discuss about vector integral theorems, then one of those theorems called Gauss Divergence Theorem we'll discuss, and then we solve some problems on Gauss Divergence Theorem. Vector integral theorems. There are three theorems known as Gauss Divergence Theorem, Green's Theorem and Stokes Theorem. And what is the advantage of these vector integral theorems? In evaluation of integrals, sometimes in multiple integrals also, sometimes it may be easier to evaluate a line integral or a double integral or a triple integral if we consider in one particular type only. For example, sometimes it may be easier when evaluated a double integral when compared to single integral. Similarly, sometimes for some particular problems, it may be easier to evaluate a triple integral when compared to line and double integral. So, if in such cases, we take the help of vector integral theorems, using which we can transform one form of integral to another form. Here, using Gauss Divergence Theorem, we can transform a surface integral to a volume integral. That means a double integral to triple integral. And using Green's and Stokes theorems, we can transform a line integral into a surface integral. So, single integration into a double integration. Now, for example, if it is required to evaluate a surface integral, we can convert that surface integral into a volume integral using Gauss Divergence Theorem, and then we can evaluate that volume integral. Similarly, instead of evaluating the line integral, we can evaluate surface integral using Green's and Stokes theorem. Green's theorem can be applied if the integrand in the line integral is in a particular format like m dx plus n dy. Then only we can apply Green's theorem. And first, I would like to state the Gauss Divergence Theorem and solve some problems on Gauss Divergence Theorem. Later, we will discuss about Green's and Stokes theorems. Gauss Divergence Theorem. Let us consider a closed region denoted by S enclosing a volume V. The region encloses a volume V. And let us consider a vector f bar which is continuously differentiable. Then the volume integral div f bar dv is equal to surface integral f bar dot n bar ds. So then Gauss Divergence Theorem states that surface integral f bar dot n bar ds is equal to the volume integral div f bar dv. So instead of finding a surface integral, we can transform it into a volume integral and we can evaluate the triple integral. And evaluation of triple integral is easier when compared to a double integral, because if you know the limits z in terms of x and y in terms of x in terms of constants, it is very easy to evaluate a volume integral. That's why we transform the given surface integral into volume integral with the help of Gauss Divergence Theorem. So here f bar is the given vector, and what is div f bar? Div f bar is the divergence of vector f bar, which can be obtained using del dot f bar, the dot product between the gradient operator and the given vector. So, which results as dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. If f bar is given in component form, simply differentiate partially the components of f bar with respect to x, y, z respectively. And n bar is the outward drawn unit normal vector to the surface S. N bar is the outward drawn unit normal vector. Let us solve some problems on Gauss Divergence Theorem. Here the problems are two types. One is to verify the Gauss Divergence Theorem and the second to use Gauss Divergence Theorem. So in problem 1, it is given to verify. So verify Gauss Divergence Theorem for the given vector taken over the surface of the cube bounded by the planes x equal to y equal to z equal to a and the coordinate planes. So what is given? Given vector function f bar is x cube minus yz I bar minus 2x square y j bar plus z k bar, and the surface is bounded by the coordinate planes. Coordinate planes means xy plane, yz plane and xz plane. On xy plane z is 0, on yz plane x is 0 and on zx plane or xz plane y is 0. So x equal to 0, y equal to 0 and z equal to 0. On the planes x equal to a, y equal to a and z equal to a. So the surface is bounded by these planes. Now to verify Gauss Divergence Theorem, we have to prove that, we have to show that the surface integral f bar dot n bar ds is equal to volume integral div f bar dv. So first you can evaluate to verify Gauss Divergence Theorem, we need to calculate both LHS and RHS. Let us start with RHS, the volume integral div f bar dv. So the given vector is in component form. So what is f1? The first component is x cube minus yz, f2 minus 2x square y and f3 is z. Let us find the partial derivatives of these components with respect to x, y and z respectively. First one with respect to x, partial 3x square and here it is constant, so 0. Dou f2 by second one with respect to y. So minus 2x square is constant, derivative of y is 1 and dou f3 by dou z is 1. So therefore, why we are calculating all these values? To find the divergence of given vector. Div f bar is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Sum of these three. So 3x square minus 2x square plus 1. Simply divergence of the given vector is x square plus 1. So we have div f bar, we can integrate. So since it is volume integral, we need to integrate with respect to x, y and z, all three variables. So if we have the limits, yes, it is very easy to evaluate volume integral. And here the limits are given by the planes. So therefore RHS is volume integral div f bar dv, which is triple integral x square plus 1 dz dy dx, and the limits are x changes from 0 to a, y from 0 to a and z from 0 to a, because the surface is bounded by the coordinate planes and the planes x equal to y equal to z equal to a. So x from 0 to a, y from 0 to a and z from 0 to a. So x from 0 to a, y from 0 to a, z from 0 to a, x square plus 1 is the divergence of f bar. First we integrate with respect to z, then y and then x. So x from 0 to a, y from 0 to a, first with respect to z. So integral dz is z. Since x square plus 1 is constant, we treat the other independent variables as constants while integrating with respect to z. So the limits from 0 to a, dy dx. So by applying the upper limit we get a, lower limit 0, a minus 0 which is a, So x from 0 to a. Now with respect to y, integral dy, since again x square plus 1 is treated as constant as we are integrating with respect to y. Here we get integral dy, which is y 0 to a dx. So again applying the upper limit, it becomes a square x from 0 to a x square plus 1 dx. Now the last integration with respect to x. So RHS is equal to a square into integral of x square dx, which is x cube by 3 plus integral dx is x from 0 to a. So a square into upper limit is a, so a cube by 3 plus a. So if you multiply a power 5 by 3 plus a cube, this is the volume integral of the given vector. Now we need to evaluate the LHS. What is LHS? Integral f bar dot n bar ds. The surface integral f bar dot n bar ds. Surface integral means over each surface of the given region, we need to evaluate the double integral. So what is the given? Given is bounded by x equal to 0, x equal to a, y equal to 0, y equal to a, and z equal to 0, z equal to a, which is a cube. So this is x axis, y axis, and z axis. Now let us draw the cube. So this is the cube bounded by the given planes, x is 0, y 0, z 0, x equal to a, y equal to a, z equal to a. Here this side, this length, let us denote the points O, A, B, C, this side, then opposite side D, E, F, G. So all 8 corners are noted by the letters A, B, C, D, E, F, G, and this is the origin O. So here this length is x equal to a, and this is y equal to a, and here it is z equal to a. Okay, now to evaluate this surface integral, we need to evaluate the double integral over each face of this cube. So that means this LHS is equal to, over the face, let us consider the face on x axis a, b, e, f, a, b, e, f, f bar dot n bar ds plus opposite face. So that means this one OCDG, OCDG, f bar dot n bar ds plus, now consider the plane on z axis DEFG, DEFG, f bar dot n bar ds plus exactly opposite one OABC, f bar dot n bar ds. Now the top one, which is on y axis, so BCDE, f bar dot n bar ds, and opposite one, the bottom one, OAFG, OAFG, f bar dot n bar ds. This is 1. So to evaluate the surface integral over the given surface, we need to evaluate the double integral over 6 faces of this cube. So one by one we need to evaluate. Let us start with the first one. Over the face A, B, E, F. So A, B, E, F, this face. Here the length is x equal to a. So here x equal to a. And since it is in YZ plane, ds is dy dz. And we know that y changes from 0 to a and z changes from 0 to a. And what is n bar in this case? N bar, for YZ plane, the outward vector is x-axis, and along x-axis the unit vector is I bar. So this direction, this is I bar. N bar is I bar. So therefore, surface integral over ABEF f bar dot n bar ds is equal to the double integral from y from 0 to a, z from 0 to a, f bar dot n bar dz dy. So we have the limits, everything we have. Now f bar dot n bar. What is the given vector? Go back. F bar dot n bar. So x cube minus yz. I bar minus 2x square y minus 2x square y j bar plus z k bar. This is f bar. Now f bar dot n bar is I bar here. So f bar dot I bar, which is x cube minus yz. This is f bar dot n bar. So let us calculate this. Y from 0 to a, z from 0 to a, x cube minus yz. So first y equal to 0 to a, first with respect to z, then with respect to y. So with respect to z, x cube z minus y z square by 2, 0 to a, then with respect to y remains. So that implies surface integral over the face ABEF f bar dot n bar ds is equal to. So here let us apply the limits. Y from 0 to a. In place of z, we need to substitute the limits. So z equal to a, upper limit is a. So ax cube minus here a square by 2y. A square y by 2 with respect to y. Now with respect to y, since ax cube is constant, integral dy remains. Integral dy is y 0 to a minus a square by 2 into y square by 2, 0 to a. And since x equal to a, this is a into a cube, a minus 0 minus a square by 4 into a square minus 0. So this is a power 4 into a power 5 minus a power 4 by 4. So here we substitute the value of x equal to a. Over the face ABEF, x equal to a. So we substitute that value also here. Similarly, for the second, over the face, exactly opposite to this face, OCDG. So here we have this point origin, at origin x0, y0, z0. Therefore, here the value of x is 0 and remaining as it is ds is dy dz, n bar is now OCDG. So for this face, outward drawn is the negative x-axis and along this the unit vector is negative I bar. So minus I bar is the outward drawn unit normal vector, minus I bar. So y from 0 to a, the limits of y and z, and what is f bar dot n bar? With minus sign we get. So previously we have calculated f bar dot n bar minus of x cube minus yz, but x is 0, so minus 0 minus yz, so y into z. So therefore surface integral over the face OCDG f bar dot n bar ds is y from 0 to a, z from 0 to a, f bar dot n bar is yz, first with respect to z, then with respect to y. Let us integrate. Integral y from 0 to a, first with respect to z. So y constant, the integral of z is z square by 2, 0 to a dy, which is by applying the limits, upper limit is a, so a square by 2 comes out, y from 0 to a, y dy, and integral of y with respect to y, so y square by 2 from 0 to a, so a power 4 by 4. This is the surface integral over the face OCDG. Similarly, let us consider the third one. Over the face D, E, F, G. D, E, F, G. This face is on Z axis and here the value of Z is A, and along this the unit vector is K bar. So K bar is the outward drawn unit normal vector. So over the face D, E, F, G, Z equal to A. Here Z equal to A and ds, this plane is in the xz plane, xy plane. So dx dy, x from 0 to a, y from 0 to a, and n bar is k bar, outward drawn unit normal vector to the face DEFG. So therefore f bar dot n bar, and we have f bar, this is f bar dot n bar is k bar. So I dot k is 0, j dot k is 0, only k bar dot k bar is 1, we get z. Here we get z, but z equal to a. So that implies surface integral over the face DEFG f bar dot n bar ds is y from 0 to a, x from 0 to a dx dy. So a constant, y from 0 to a, integral dx is x, limits are 0 to a. So upper limit is a, so a square, and last integration is with respect to y, integral dy is y. So a square into y 0 to a. So finally we get the answer for the face DEFG, the surface integral is a cube. Similarly, the fourth one, opposite to this face DEFG, opposite to DEFG, that is OABC, OABC. And since this origin is there, here the value of z is 0 and remaining as it is ds is dx dy, x changes from 0 to a and y from 0 to a, and the n bar for this face is the negative k bar, because the negative z axis is the outward drawn axis. So n bar is outward drawn unit normal vector. Along that axis, negative z axis, the unit vector is minus k bar. So therefore f bar dot n bar is minus z, but z is here at this face, z is 0. So therefore that implies over the face OABC, f bar dot n bar ds is equal to x from 0 to a, y from 0 to a, 0 dy dx. So the answer is 0. Similarly, the fifth one is over the face BCDE, which is on y axis, BCDE. Over BCDE, so which is on y axis. So here the value of y is a and it is on xz plane, so ds is dx dz, x and z changes from 0 to a, and for this face the outward drawn unit normal vector is j bar. So therefore we need to calculate f bar dot j bar to find f bar dot n bar. And what is the vector? Minus 2x square y is the component of z, minus 2x square y. So minus 2x square y, and since y is a, so our f bar dot n bar is minus 2ax square. So that implies surface integral over the face BCDE, f bar dot n bar ds is x from 0 to a, z from 0 to a, minus 2a into x square dz dx. So minus 2a is the constant and x from 0 to a. First we need to integrate with respect to z. Since x square is, we treat x square as constant, integral dz is z from 0 to a, and applying the limits we get minus 2a square, and again with respect to x, so here x square, so integral x from 0 to a x square dx, so which is minus 2a square into integral x square is x cube by 3 from 0 to a. Only the upper limit is non-zero, lower limit is 0. So minus 2a square into, we get a cube by 3, see, which is minus 2a power 5 by 3. Similarly, for the opposite face, for this BCDE, OAFG, over the face OAFG, here since the origin is there, at origin the value of y is 0 and ds is the same dx dz, x varies from 0 to a and z varies from 0 to a, and here outward drawn unit normal vector is the negative j bar, and therefore f bar dot n bar is plus 2x square y, but y is 0. Therefore, surface integral over OAFG f bar dot n bar becomes 0. Finally, the LHS is surface integral f bar dot n bar ds. We need to add all these 6 values. Let us go back. For the first one, we got a power 5 minus a power 4 by 4. A power 5 minus a power 4 by 4. Second one, a power plus a power 4 by 4. Third is a cube, plus fourth is 0. Fifth is minus 2a power 5 by 3, and sixth is 0. So here again these two 0. So a cube plus a power 5 common, 1 minus 2 by 3. So which is 3 minus 2, 1 by 3, a cube plus a power 5 by 3. Let us go back and check whether RHS is the same or not. A power 5 by 3 plus a cube. A power 5 by 3 plus a cube. Hence, LHS equal to RHS and Gauss Divergence Theorem. So, therefore, LHS is equal to RHS and hence Gauss Divergence Theorem is verified. So, like this, to verify the given theorem, we need to find both LHS and RHS, and finally we need to prove that both the values are same. Coming to the summary of today's session, today I have introduced the vector integral theorems. Vector integral theorems. There are 3 theorems: Gauss Divergence Theorem, Green's Theorem and Stokes Theorem. And today we discussed about the Gauss Divergence Theorem. We have solved a problem on Gauss Divergence Theorem. This is for today's session, and in the next session we will solve some more problems on the same. So, problems on Gauss Divergence Theorem. Thank you.